this series of the kinetic theory and gaseous system, as an application of this kinetic equation, I shall discuss today the molar heat capacity of ideal gas. Heat capacity is defined as the amount of heat required to raise the temperature of the substance by 1 degree. So you can see, larger the amount of this substance, greater will be the heat capacity. And it is the heat capacity also depends on nature of the nature of the substances. Some substance can store up much more heat for the rise of 1 degree temperature for the same amount of the substance. So it is the nature of this substance which can retain the more amount of heat with higher heat capacities. Today, I shall limit my discussion only for the ideal gas. So it is heat capacity of this ideal gas could be defined as the amount of heat required to raise the temperature of this ideal gas by 1 degree. If heat capacity is naturally extensive property, as mass is not defined. If we define the amount of the substance, amount of this gas, then it becomes an intensive property. If we define the amount of this gas 1 gram, then it is called the specific heat or specific heat capacity. If we consider the 1 mole of this gas, then it will be the molar heat capacity of this gas. And specific heat or molar heat capacity, these are intensive properties as mass are defined. So actually, if we in case of a gas, there are 2 types of heat capacities, 2 types of molar heat capacities, or 2 types of specific heat capacities. Molar heat capacity is at constant pressure and molar heat capacity is at constant volume. So molar heat capacity volume is defined as Cp. How it is defined? It is the amount of heat required for 1 mole of this gas to raise the temperature by 1 degree, provided volume will remain constant. And this is capital Cp. Similarly, molar heat capacities at constant pressure. If pressure has been kept constant, then it will be Cp. These are the molar heat capacities, Cp and Cv. In case of a solid or liquid, these 2 are same, as the effect of pressure on the volumes for the solid and liquid are minimum or negligibly small. And if we call the specific heat at constant volume, if we design the specific heat at constant volume as small Cv and specific heat at constant pressure equal to small Cp, then naturally that the Cv equal to molar mass of this gas into Cv, and Cp is equal to molar mass into Cp. So these are the relations between the molar heat capacities and the specific heats of a substance, of a gas. If we consider, if we picturize this Cp and Cv, then it could be seen that Cp is greater than Cv. How could we do it? Let us draw two diagrams. This is the vessel, and here V, it is the piston, and here the V is constant. V is constant. It contains 1 mole of this ideal gas, and the temperature is raised from T to T plus 1. So it is the amount of heat required to raise 1 mole of this gas from T to T plus 1 at constant volume. It is Cv. It is Cv. Molar heat capacities at constant volume. So it is the amount of heat required for 1 mole of the gas to raise the temperature by 1 degree, T to T plus 1. Similarly, if we draw another diagram, say this is volume V1, here P is constant. Here P is constant. So temperature is raised from T to T plus 1. Here also contains 1 mole of this ideal gas. We are confined with the discussions of one of this ideal gas. And in this case, whenever the pressure remains constant, temperature is raised by 1 degree. So according to the Charles law, the volume will increase. Say volume V1 to V2. So whenever the volume of this gas is increased, then there will be some additional work. Here the amount of heat is equal to Cp. Cp is the amount of heat required to raise the temperature of 1 mole gas from T to T plus 1 by 1 degree, where P remains constant. So if we compare this Cp and Cv, then here also temperature is raised by 1 degree, here also temperature is raised by 1 degree, but here the additional heat will be absorbed for the expansion of this gas, and so this Cp minus Cv. So Cp is greater than Cv. Cp is greater than Cv. how much the difference, how much greater, then Cp minus Cv, you can write the mechanical work done, W done by this gas, and for that amount, for that doing work, additional amount of heat will be absorbed. And this one could be written as P into del P into del pressure into volume change. Or you can write P V2 minus P V1. V2 is the final volume, V1 is the initial volume. So this is equal to R T plus 1 PV2 equal to final temperature R 1 mole gas T plus 1, and minus when the temperature, initial temperature was T, then it is R. So if we do this one, this is equal to R. So Cp minus Cv is equal to R. So Cp is greater than Cv by R amount. If we use this unit calorie, then R equal to, then Cp minus Cv equal to 2 calories per mole per Kelvin temperature. So naturally, it is. However, I can remind you that it is only valid for this ideal gas. If we consider the real gas, suppose van der Waals gas is the representative of this real gas, then I have shown in thermodynamical chapter, in my video lectures on thermodynamics, chemical thermodynamics, that for real gases, Cp minus Cv is greater than R. Greater than R. And different gases, the difference will also be different. But here for this ideal gas, Cp minus Cv equal to R. Now let us, now I can write here this Cp minus Cv equal to R. Now let us consider given magnitude of Cp and Cv. What will be the value of Cp? What will be the value of Cv for this ideal gas? Let us consider the Cv. What will be the value of Cv? This is the heat given to raise the temperature of 1 mole gas from P to T plus 1. Just to see this amount of heat will increase the translational kinetic energy of the molecules. Translational means whenever the molecules are moving, translational motions of this molecule means the molecule will move from one place to another place in space. Molecule as a whole moving from one place to another place within this vessel. So with this increase of temperature, the kinetic energy, translational kinetic energy will also increase. This amount of heat will increase the kinetic energy of 1 mole gas from T to T plus 1. And in my last class I have shown that the kinetic energy of 1 mole of this gas equal to 3 by 2 RT. 3 by 2 RT. This is translational kinetic energy of the molecules. So this is Cv equal to 3 by 2 R final temperature T plus 1 minus initial temperature 3 by 2 R. This is the kinetic energy at its temperature T plus 1 when this temperature is increased by 1 degree, and 3 by 2 RT, it is the kinetic energy when the temperature was T. So the reference, this is the amount of heat required to raise the temperature by 1 degree. And in addition to this one, there is another type of motions within the molecules. This is called intramolecular energy, or the internal motion of the molecules, and due to internal motion of the molecules, there is some additional increase of energy, and this has to be supplied from here. So let us take this x. X is increase of intramolecular energy of 1 mole gas for rise of 1 degree. This is the increase of intramolecular energy. This X is the increase of intramolecular energy. Intramolecular means the energy within the molecule. So this is the X. So this one gives that 3 by 2 R plus X R plus X. Now let us calculate the value of X. Actually, in case of molecules, molecular motion, it is the translational motion. And this the increase of kinetic energy for this translational motion of 1 mole gas for 1 degree rise in temperature is a 3 by 2 R. And these two, and another is the rotational motion. Rotational motion means the motion of the atoms within the molecule. This is the intramolecular motions. And another is vibrational motion. Vibrational motion. So these two are called the intramolecular motions, and for 1 degree rise in temperature of 1 mole gas, these two energies will also be increased. Rotational motions I can picturize as, suppose this is diatomic molecule. Diatomic molecule, 2 atoms are there within the molecule, and this is the center of gravity. This is the center of gravity, or you can say center of gravity or center of mass. And if we draw an axis, if it is the x-axis, it is the x-axis, then this molecule, the atoms within the molecule will rotate. In this fashion. Suppose here is atom, this is the axis passing through the center of gravity, and this will move, this will rotate along this z axis. Similarly, for the case of diatomic molecules, it can rotate along this two independent axes. I have shown it is the rotation of the molecules along the z axis, and if we consider this y axis, then it can also rotate along this y axis independently. If we can take this x axis as the bond axis have been taken as the x-axis, then whenever the diatomic molecule moves in this way, there will be no change of configuration or no change of position of the molecules in space while it is rotating. So actually for this diatomic molecules, there are rotations in two independent axes. In each independent axis, actually the magnitude is half kT per molecule, or half RT for 1 mole of this gas. So in two axes, for the diatomic molecules, for these two axes, this kinetic energy for rotation of 1 mole gas equal to half RT plus a half RT, and this is equal to RT per mole. So if we rise this 1 degree temperature, then increase of increase of rotational energy equal to R T plus 1 minus RT. This is equal to R, and this is the value of X. This is the value of X for this diatomic molecule. And for triatomic molecules, this like the water vapor, carbon dioxide, in this case, or in polyatomic molecules, there will be 3 independent axes of rotations along this x-axis, along the y-axis, along the z-axis. In this case, or suppose for water, suppose for water, this is H. So if this has been taken as the bond axis, then while we are rotating along this bond axis, this hydrogen atom will also change space while this water molecule is rotating. So in case of polyatomic molecules, every polyatomic molecules, it can rotate in 3 independent axes, along the x-axis, along the y-axis, along the z-axis. So for polyatomic, so it is for diatomic molecule. Diatomic molecule means the molecule contains these 2 atoms only. For polyatomic molecules, molecules, for polyatomic molecules, E rotation equal to half RT plus half RT plus half RT. So equal to 3 by 2. 3 by 2 RT. So x equal to delta E rotation equal to 3 by 2 R T plus 1 minus 3 by 2 RT equal to 3 by 2 R. So for polyatomic molecules, this x equal to 3 by 2 R. And this vibrational motions, there will be also vibrational motions. The molecule atoms within the molecules will vibrate. Suppose for diatomic molecules, this is one, and this is the center of gravity. This is the axis. Center of gravity remains unchanged, and the atoms will be, this is the equilibrium position, elongated, and coming again equilibrium position, and then compressed. So by this way, the two atoms within this molecule will vibrate continuously. This is the equilibrium axis, equilibrium bond distance, then elongated, again coming equilibrium, then compressed, then again equilibrium, then again elongated. This is one complete rotation. And in case of for one mode of rotations, for one axis, vibrational energy per mole, vibrational energy per mole equal to RT for one mode. So in case of diatomic molecules, there will be only one mode, it will be RT. But in this case, with the change of temperature not very high, for small change in temperature of this gas, the vibrational energy or no heat will be absorbed for this increase of kinetic energy of this vibrational motions. To increase the vibrational energy, large amount of heat is required, and this can only happen at high temperature. We shall discuss in more details while we focus the law of equipartition of energy. In this case, the translational motions, rotational motions, vibrational motions will be elaborately discussed. And in that context, we shall come the degrees of freedom or independent degrees of freedom. So here this one is the only translational kinetic energy, and X is due to these two. But if we ignore, if the vibrational energy does not contribute to the CV value, then only the rotational energy will contribute, and X will be equal to R for the diatomic molecules. X will be equal to 3 by 2 R for the polyatomic molecules, and for monoatomic molecules there will be neither the rotation nor the vibration, only translational motions. So now we consider the Cp and Cv values. monoatomic gas. Monoatomic gas means the molecule constitutes only one atom. Only one atom. Such as inert gases, metal vapors like sodium vapors, mercury vapors, and so on. In case of monoatomic gases, this x equal to 0. X equal to 0. Neither the rotational motions nor the vibrational motions. Only it has the translational motions. So in this case, a CV equal to 3 by 2 R. 3 by 2 R. And x equal to 0. So CP naturally R will be added. R will be added to the CV value. So it will be 5 by 2 R. And so CP by CV equal to 5 by 2 R divided by 3 by 2 R equal to 5 by 3 equal to 1.66. Whenever this one is taken as the gamma. Gamma is the molar heat capacity ratio. Gamma is the molar heat capacity ratio. So gamma is equal to 1.66 for monoatomic gases. Gamma could be determined experimentally. Gamma could be determined experimentally by measuring the velocity of sound. And gamma actually the velocity of sound is equal to root over of gamma RT by M. M the molar mass, T the temperature, gamma the molar heat capacity ratio, and V the velocity of sound. By measuring the velocity of sound in a gas, this gamma in a gas at a temperature T and the gas having the molar mass M, the gamma could be determined. R is the universal gas constant. So if you get this value of gamma, and if the value of gamma is 1.66, then it is definitely the monoatomic gas. For diatomic gas, like oxygen, nitrogen, carbon monoxide, etc. Here is the helium, neon, sodium vapor, etc. So in this case, CV equal to 3 by 2 R and plus x equal to this x equal to R for diatomic molecules. So R. So this is equal to 5 by 2 R. And CP equal to 5 by 2 R plus R equal to 7 by 2 R. So this gamma is equal to 7 by 2 R divided by 5 by 2 R, and this is equal to 7 by 5 and equal to 1.40. So if the value of gamma is found experimentally 1.40, then it will be the diatomic molecule. And for polyatomic molecules, x equal to 3 by 2 R. 3 by 2 R. So 3 by 2 R. So CV 3 by 2 R. So CV equal to 3 by 2 R plus 3 by 2 R equal to 3R and Cp equal to 4R. So gamma is equal to 4R divided by 3R equal to 1.33. So this is for the monoatomic it is 1.66, for diatomic it is 1.40, for polyatomic it is 1.33. I have discussed that the vibrational energy does not contribute to the value of Cv at ordinary temperatures. But if the temperature, and also in these expressions you see that Cv or Cp, they are independent of temperatures. So long we have limitations that the vibrational energy does not contribute to the Cv or Cp value. But at high temperature, the temperature will affect the value of Cp and Cv. With the increase in temperature, the Cp and Cv value will also be increased as vibrational energy begins to contribute. So in that case, the value of gamma is found to be less than it would be calculated with ignoring the vibrational motions. This is discussed in quantum mechanics. Actually, vibrational energy levels are very large. So, large increase in temperature is required to transit this molecule from one vibrational level to another vibrational level. So, these are the all regarding the molar heat capacity of this ideal gas. One problem I can give you here. This problem so these formulas are very important, and this gamma equal to Cp by Cv, and this is equal to 1.66 for monoatomic, gamma equal to 1.66 for monoatomic, equal to 1.40 for diatomic, and it is 1.33 for polyatomic gas. These two data are very important. So let us give a very simple problem. The specific heat problem, specific heat at constant pressure and at constant volume of a gas are 1 point or 0.125 calorie, gram inverse and Kelvin inverse, and 0.075 calorie, gram inverse and Kelvin inverse respectively. Only these two data are given. Means small cv, small cp solution. Find molar mass of the gas, molar mass and atomicity of the gas. This is the questions. These are the data. Two data are given, and this is the two questions: molar mass and the atomicity. Atomicity means how many atoms are forming this molecule. So in this case, these two we know the solutions to the problem. This is Cp minus Cv equal to R. So instead of Cp, we can write this M into small cp minus M into small cv, and this is equal to R. This is the molar mass, and these are the specific heats. These are the molar heat capacities. So M you can get common, small cp minus small cv equal to R. So M equal to R by small cp minus small cv. If you put this one, as cp and cv are in calories, so here this R is 2 calorie mole inverse, Kelvin inverse, and divided by this one is 0.125 minus 0.075. It is also calorie, gram inverse, Kelvin inverse. Calorie cancels, Kelvin inverse cancels, and the value is coming to be 40. 2 by 0.05, 40 gram mole inverse. So this is the molar mass. If you consider this atomicity, if you try to get this atomicity, how many atoms forming this molecule, then gamma equal to Cp by Cv, or M into small cp divided by M into small cv. And M cancel, small cp by small cv 0.125 divided by 0.075 calorie. Both the units are same, in unit will be cancelled, so this will be equal to 5 by 3 or 1.66. So the gamma value is 1.66. Molar mass 1.66 means it is monoatomic. So the gas is monoatomic. Molar mass is 40. So naturally you can see the gas is argon. This gas is argon. The gas is argon, ArGON, whose molar mass is 40 and it is also monoatomic. So this is all about the preliminary discussions of the value of this molar heat capacities. We shall again discuss the molar heat capacities of this gas while we discuss the law of equipartition of energy. So this is in my next class I shall start the background behind the formulations of the Maxwell's distribution law. Maxwell's distribution of speeds among the molecules, of course, for the ideal gas. This chapter only confined with this ideal gas only, ideal gas. So this is all about my today's lecture, and in my next class I shall discuss the background or preliminary items to reach the Maxwell's distribution of velocities among the molecules. So thank you all.